Now, next question is question 67. This is from the topic of locus. First, we need to construct a triangle ABC such that AB is 7 centimeter, BC 6 centimeter, and CA 5 centimeter. Use ruler and compass. Then, draw the locus of the point such that it is equidistant from BC and BA, number 1. And number 2, it is equidistant from points A and B. Then mark P where the loci 1 and 2 meet, measure and write the length of PA. Okay, so whenever we have a constructions based question, it's a good practice to have a rough diagram ready by reading the description of the question. So first I need a triangle ABC with some side measurements. Then they're asking about some locus of points equidistant from the intersecting lines BC and BA. So according to the locus theorem, we know that the locus of a point equidistant from two intersecting lines is the bisector of the angle between them. So the angle between BC and BA is angle B. So I need to draw the bisector of angle B. That will be the locus for part 1. And then for part 2, locus of points equidistant from fixed points A and B. We know that locus of such a point will be the perpendicular bisector of the line segment joining them. So I have the point AB. So I have to draw the perpendicular bisector of AB. And then the angle bisector and perpendicular bisector will meet at some point. We have to label that as P, and then we have to measure and write the length of PA. So this is my rough figure based on the description. Then I will start the actual construction. So I'll take a scale. First I can draw the base BC, which is 6 centimeters. So I'll take a scale and draw a line segment of length 6 centimeter. Okay. So this is BC of length 6 centimeter. Then I need the other two sides, which are 7 centimeter and 5 centimeter. So let me take my compass and then measure a length of 7 centimeter. Okay. So BA is 7 centimeter. So from point B, I will draw an arc somewhere here. The arcs should not be very dark, but at least it should be visible. And then the other side is CA 5 centimeter. So I'll take a length of 5 centimeter and center at point C. I will try to cut the previous arc. So I get the point of intersection. So that point is point A. So I have to join AB. So you'll see that AB will be 7 centimeter. And AC will be 5 centimeter. So construction of triangle ABC is completed. Then I need to draw the locus of points equidistant from BC and BA, which I have told you is the bisector of angle B. So I have to take my compass and choose any suitable radius. And then I need to cut the arms of the angle. AB and BC are the arms. I have to cut it with an arc. So let's say this is my arc, and it cuts the line segment AB and BC at 2 points. So from this point, I will draw another arc somewhere here, and with the same radius, I'll put the center here, and I'll cut the previous arc. So then the point of intersection of the arcs I will locate, and then I will join point P with that intersection point using a scale. So this is the locus of points for part 1, equidistant from BA and BC. Then the second locus we have discussed is the bisector of line segment AB. So I'll take my center. Radius should be more than half the length of AB. Draw an arc over here and over here. Okay. Then with the same radius, center at point B, cut the previous arcs. So it cuts the arc here and here. So then I will join these 2 points. This point and this point. So this is the perpendicular bisector of AB. Now the angle bisector and perpendicular bisector intersect at this point. So I'll call this as point P. And then I have to measure the length AP. So I will take a scale and I'll join AP first. And then I'll take the measurement. So when I'm taking it, it's coming up to be approximately about 3.8. Okay, so below the construction I have to write some details. I need to write the answer for the locus. So part A1, locus of points equidistant from BC and BA. I have to write it is bisector of angle ABC. If you want to label, let's say this point is D, so that is BD. And then for part 2, the locus of points equidistant from AB, the points A and B, is the perpendicular bisector of AB. If you want to label, we can say this is EF. And then they meet at point P, and the length of PA was 3.8 centimeter. Okay, done. Next, moving ahead to question number 68. Okay, so this is from circles and tangents. In the given figure, O is the center. ABCD is a quadrilateral where the sides touch the circle at EFGH. Then length of AB, BC and AD are given. We have to find the length of CD. Okay, so for this question, the main theorem that we will use is that from any exterior point, the length of two tangents are equal. So I have CF, CG equal tangents, DH, DG equal tangents, AH, AE equal, BF and BE are equal. I want to find the entire length of DC. So let me take DG as X and GC as Y. Then I want to find what is X plus Y. Okay, now if DG is X, DH is also X. And then AH will be 24 minus X. And AH is same as AE, so AE is also 24 minus X. CG is Y, so CF will also be Y. Now BF is BC minus CF, so it will be 18 minus Y. BF is same as BE, so BE is also 18 minus Y. Then finally, I will look at the length of AB. AB length is given 15, which will be 24 minus X plus 18 minus Y. From there, I will get some equation with X and Y and try to find out what is X plus Y. So I have written all the steps here. So starting with this theorem, I have to state the theorem that I am using. Two tangents from an exterior point to a circle are equal. And then I have written down what are the pairs of equal tangents. And finally, I get an equation where I am looking at the length of AB. So 15 is equal to 24 plus X plus 18 minus y. And if I solve it, I get the value of x plus y as 27. And then from the figure, the length of CD is also x plus y, which will be 27 centimeter. So that's my final answer. Moving ahead to the next question. So ABCDEF is a regular hexagon inscribed in a circle with center O. PQ is a tangent to the circle at D. Find the value of these three angles. So one important property of a regular hexagon is that all the interior angles are 120 degree. Now FAG is an exterior angle. So if I look at interior angle FAB, that was 120 degree, and then the interior angle and the exterior angle form a linear pair. Okay. So then your angle FAG will be 180 minus 120, which is 60 degree. Then BCD is another interior angle of the regular hexagon, which will be 120 degree. So BCD also found. Then for angle PDE, PDE is the angle between tangent PD and the chord ED, that is angle PDE. So we know that angle between a tangent and a chord is equal to the angle in the alternate segment. So the chord ED is making angle EFD in the alternate segment. So this PDE will be same as angle EFD. So now let's focus on how to find angle EFD. We know that this angle E is part of your regular hexagon, interior angle of regular hexagon. So this is 120 degree, and EF is equal to ED because they are the sides of the regular hexagon which are equal. Then if I look at triangle EFD, it's an isosceles triangle where, let's say, the base angles are X and X. So then I can apply angle sum property to say that X plus 120 is 180. So I will find that the value of X will be 30 degree. So 30, 30, 120. So if this is 30 degree, EFD is 30 degree, then PDE also has to be 30 degree. So all the three angles will be found. And if you have to write the statement and reasons, you can write something like this. So mention that interior angles of a regular hexagon is 120. Then one reasoning was linear pair, and then angle in alternate segment. Then base angles of isosceles triangle, angle sum property. So all the three answers. Then moving ahead to question number 70, we have AB and CD intersect at the center O of the circle. So AB and CD intersect at point O. I can see that AB is a straight line passing through the center. So that means AB is also a diameter. We can use that in our solution. Then angle EBA is 33, EAC is 82. Find these three missing angles. So let's look at angle BAE. BAE. So this angle. Okay. I can say that since AB is a diameter, angle AEB has to be 90 degree. Then I can look at triangle EAB. One is 33 degree, another is 90 degree. Then according to angle sum property, angle EAB plus 33 plus 90 is 180. So EAB measure will be 57 degree. EAB will be 57 degree. Then I have to find BOC. BOC. So for that I can find first BAC. Now full angle EAC, full angle A is 82 degree, EAB is 57 degree. So then BAC will be full 82 minus 57. So 82 minus 57 is 25 degree. So BAC is 25, then BOC will be double of BAC, because BOC is the angle subtended by the arc BC at the center, which will be double the angle at the remaining part of the circle. So BOC is double of 25, which is 50 degree. Okay, so that is also done. Then the last one is angle ODB, this angle ODB. Then let me look at angle AOD. AOD is vertically opposite to angle BOC. So AOD will be 50 degree, and BOD AOD is on a straight line, so it forms a linear pair. So this angle BOD will be 180 minus 50, which is 130. Then if I look at triangle DOB, I have 130 degree, 33 degree, and this unknown angle. So the angle sum will be 180. So 130 plus 33 is 163. So then 180 minus 163, this angle will be 17 degree. So ODB will be 17. And again, I have written the statements and reasons here. So some of the theorems used: angle in a semicircle, angle sum property, angle subtended by an arc at the center is 2 times the angle at the remaining part of the circle. Then vertically opposite angle linear pair, like that. And the last part was ODB is 17 degree. So we need to write all the statement and reason, and the answers to the subparts should be clearly highlighted.